What happen is that I'll give the word to the three persons from the committee, the examinators, and after that I'll give the word to the supervisors if they have any questions, and after that again there could be some questions from the audience ex auditorio who wishes to ask questions, and I know already there's at least one. Ooh. Where are you? There, yeah. Good. But we will come back to that. So, in the first place, I will give the word to Per Johan Brandvik, right? And you have got a microphone on?
Yes.
Good. And therefore, I will, the candidate may remain standing there. And, yeah, you can start.
Yeah, thank you. Do you hear me? Yeah, good. Being a Norwegian in Denmark is always pleasant. And when I was a kid, in one time when I grew up, I realized that my fairy tales from when I was little, some of them were actually coming from Denmark through some common Scandinavian poets. So fairy tales are important for both of us. And in a way, this is like a fairy tale or a show or a drama. Yeah, and in this drama, the opponents are not the nice guys. Yeah. We are actually paid to be difficult. Yeah. We are actually brought here for just one purpose, to question and ask the difficult questions. Yeah. And I've read this thesis quite in details. And we have already said in our statement, and this is it's an excellent thesis. But however, we have some comments and some questions. And I marked my nice comments in green and my difficult questions in red, and you can see this is, yeah. So let's start, but I don't expect your mother to like me. That's not that's not why I'm here. So I'm a chemist, and I've been involved in-situ burning from a chemical point of view. Oil properties, why do they burn? Why do they ignite? Why don't they ignite? I worked in the lab and in the field. So to start with the test system, you have used a test system which is developed based on an earlier system, which I have used and which also were brought here to Denmark by Janne. Yeah. And there are some very nice features with the new systems, which I really enjoy. So, could you just explain or tell us the main reason for developing the new system and the advantages with it?
Yeah, sure. So the first version of the new system is this one, the COFA. So one of the main advantages compared to the old system, so for the audience, the old system was a holder where there was, basically it was just a cylinder with water flowing through it and some water below it, if I'm correct, and there the oil. So it looked like just the Pyrex cylinder without the larger water body around it. One of the things that is different in this system is that the Pyrex cylinder has a hollow bottom. So therefore, when the oil surface starts to decline, the water will flow in to compensate for that amount of weight, so we can measure the surface temperature for a longer amount of time. There's still a height difference, especially if you go to slick thicknesses of say, 20 or 40 millimeter at the start. But for 5 or 10 millimeters, you can pretty much measure the surface temperature throughout the whole burning time. And if you have just a steady water column, your oil slick will always decrease in height, and then it becomes very difficult to measure that surface temperature. So that's one of the advantages of this system. The second is that we have a larger water body. We don't have artificially water cooling the water and oil inside our burn. So we have a more natural heat losses and cooling of the oil. With the scale, we also have a higher amount of water, or compared to the original burning cell that you have used. And basically, you could claim that it's about the same as the old burning cell, but one of the main advantages is that you don't have a flow, and a flow can actually disrupt the measuring of the weight. And that was one of the problems we had with the cone calorimeter, the setup where the water was flowing. I could not get a burning rate from that because the flow varied so much the weight of that whole setup that outweighed, so to say, the difference of oil burning. So with this, we actually can cool the oil while burning it and measure the burning rate. So then, but I still found that there were issues with this setup. And one of the main issues is that you have this very high Pyrex cylinder. That was a design choice that was made early on, but looking at it from once we studied the boil over and realized, well, this is really affecting our experiments, looked into how can we prevent that, what is the difference. So I'll just look up the slide with the new one. No. There. So that's when we made the short Pyrex cylinder. It's still high enough to contain the oil, but when adding a propeller to the water basin, we get a current in there, and we can actually mimic the current you see in in-situ burning on sea. So we get a little bit closer to properly scaling this setup. And the final iteration, which I have not been able to use in my PhD, but which I developed during my PhD, I got all the components, the ideas, is to add the extra heat to it. So then it looks like this, where we would surround the oil by infrared heaters that do the same as what we get in the cone calorimeter, but there you have this water flow that is not really the same as a natural heat losses to the water layer. So this is another step closer to small-scale experiments that properly simulate large-scale experiments. The only thing is, like we saw with the cone, there is this about 10 to 20% burning efficiency difference that we cannot account for due to the scale. So I have not been able to use this yet, this setup, but I expect that the highest burning efficiencies we can get are around 80%, unless we go very high and force the burning efficiency, so to say, by using an extra heat flux.
But you correlated results with the new and the COFA and the older system. What did you find?
Well, I have not correlated so much those results myself. Those were done already before I started my PhD. So the setup was calibrated, so to say, based on the experiments you did in the small setup, but also the one in the larger, and that mainly focused on the ignition. So how does the ignition work in those systems? Do they work the same? And not as much on if we burn the same type of oil, does it have the same burning rate, same flame height? So more ignition and practical than actual fire parameters.
So I see many advantages with the new COFA system, but could you see any disadvantages compared to the earlier system?
Well, the heat losses you can't really, or are much harder to measure in this system. What you could do with the old system is, if you know very well what goes in your water and what goes out your water, you would measure that in high detail. You could maybe calculate the heat losses to that water layer and say, okay, so much, this is how much I lose. And that is what we try to do with the cone calorimeter. We got to a rough estimate of the heat losses, but they were so high compared to the amount of heat we applied that there's clearly something in our calculations that needs refinement. So basically I would say that we took the things from that old system in our cone setup with the heat, with the flow, which was one of the main advantages I would say in that small setup, and then the other part of a more natural heat losses to the water layer in this setup, where we can also add the extra lamps and have a current to prevent boil over, but still burn it on water.
Okay. One advantage I could actually think of now is that the old system you could take out of the lab and actually use it out in the field.
Of course, yes.
We have some nice studies where we actually are sitting on the ice, sampling and using them.
Yeah, it was mainly made for ignitability, and therefore it's actually very well suited. You can see, can I ignite an oil? So sorry, in that aspect, it's easier to use for ignitability tests, but those I have not really studied on in this setup that I use the cone for.
But one last question regarding the system. On page 44.
Yeah, I'll just open the... That's not page 44. Ah.
Yeah. Your definition of burning efficiency, I find slightly strange. Could you explain why you have used this definition?
I'm pretty sure it's similar to what you have used in Syntev, maybe in a different formula. But what I use is I have an amount of oil on the water surface.
Yep.
So basically the oil spill. I burn some amount of that. I collect the weight of the residue and see how much do I have left. And everything that has been burned is the burning efficiency. So it purely looks at how much can we remove from the water surface.
Yes, but that's not what's written there. You have the mass of the residue over the initial mass.
Yeah.
So if you haven't burned anything, if you have zero efficiency, the residue is the same as the starting point. This actually becomes 100%.
Yes,
So
this is
the opposite of what you actually use.
Correct. This is a mistake. It should be the initial mass minus the residue mass divided by the residue mass times 100%.
That's what others use, and that's actually what you have used, but it's not what's written here.
Indeed. Yes, I will correct that before printing.
It should absolutely be corrected. Okay, let's move over to the oil types. The oil types you have used?
Yeah.
I'm an oil chemist.
Yeah.
And selecting oil types are always important. It's not the number of oils you have used. People often brag that they have used 20 oil types, but they could be so similar that actually you are using one oil type. So, but you have, can you explain the strategy behind your selection of oil types? You have used both what you call fire liquids, or?
So these are, I think, all of the oils I've used during my PhD study. So I will just walk through this table from top to bottom.
Yeah, we don't have to have need to.
You just care about
all the details in the table, but just tell us why have you selected those oils?
So I started out with the pure components as a baseline to how I believed crude oils would not behave. Yeah. So if I burn them in a certain way, the crude oils should behave differently. Yeah. So that's a baseline for all my experimental setups.
That's a good choice.
Then I will go through like the order I used them actually during the work of my PhD. The Duke and Repco are both light crude oils. relatively speaking. So they have a high amount of volatile components. And I used both of them to see how similar do light crude oils burn. And I saw from most of the experimental data that they're actually rather similar. Surface temperatures have maybe a few tens of degrees on top of 100 different. So that was nice to be able to confirm for myself. I can categorize oils by saying it's light or it's heavy. And if it's light, it doesn't matter exactly what it is because it burns in a similar fashion. ANS was the crude oil I used during my external stay in the US. Was also a light crude oil. That was not a conscious choice to use that specific oil. That was mainly governed by availability. But it also allowed me to say, okay, I have a crude oil here that is light. And I can compare it to the same crude oils I burn at home because it's actually rather close to the physical and chemical parameters of REPCO. So the experiments I do in the US, even though they're very different conditions because I did those in ice, I can still use them to compare somewhat the results with my results in the lab with different types of oil. Then, because we got into this volatility controlled order, we also wanted to use oils that have different type of composition than just the light crude oils to test if you have a crude oil with higher amount of high boiling point components, like grana, do you indeed get lower boiling points? And that was shown both in the cone and the COFA that indeed we get lower boiling points, lower burning efficiencies. And then finally the IFO is a refined oil, so it has hardly any light components. And this was by far the hardest to burn, hardest to ignite. And it was interesting to see in the cone when we get to these high heat fluxes where the burning efficiency actually does get high, the residue is just solid. It's not even remotely solid liquid, it's just solid and you have to scrape it out.
Yeah. Good, and I agree. The selection of oils are quite good. It spans out a lot of the interesting and essential properties we want to study. And as you stated in your presentation, what is the main limitation of operational in-situ burning?
Basically the capacity of burning oil.
Before you...
Okay, before you actually manage to ignite the spill, then it would be ignitability of the crude oil.
Yes. So ignitability should be quite central in our work, which has the objective to predict if the oil is going to burn or not. Yeah. So and ignitability is very dependent of
weathering.
Yes. So when you then selected one oil to extend your weathering variable.
I used one of the light crude oils to weather. From an emulsion point of view, a light crude oil is not optimal because it makes less stable emulsions. But that is why I kept shaking the emulsion constantly to still have, even though it has been standing for some time, shake it beforehand. And I tested different times of shaking beforehand and letting it stand to see what the effects of that were. So I'm reasonably confident that by shaking it, the emulsion was an actual emulsion at the time of burning. But definitely part of the future work is to also start weathering and emulsifying grana to see how that would behave under ignitability studies.
If we look on table 3.4 on page 55, this is the physical properties of the duck oil and the weathering. And in the experimental part, you have described how you are doing the weathering.
Yeah.
And but if we look on the viscosity here, this low viscosity screams out that this is actually not a real emulsion. This is just a slurry of oil and water.
Yes, that
Yeah.
could be. Also, the method to measure this viscosity is highly variable for this emulsion because it's not stable enough to last for half an hour it almost takes to do the measurement for viscosity measures with these Anton Par viscometer.
Yeah. But I think of all the oil you have in your broad selection, this is the least best candidate for making emulsions.
Yeah.
Yeah. And I have this note in the marg here. Where was Janne? Because one of your supervisor has lots of skills in this, and I think if you have selected one of the others, this would have been much more successful.
Yeah. Well, it's definitely the idea to extend this study and incorporate the other oil as well.
And there are already studies performed on the weathering properties of this Dutch underground consortium oil, which are available. So you could actually have found how this oil reacts and what makes it stable or not.
Yeah, well, it is a light crude oil, so almost by categorizing it as a light crude oil, the emulsification is not as successful as, for example, grana.
Yeah, but for many light oil emulsifies and form stable and good emulsions. And emulsions, they are either stabilized by
resin. Oh yeah.
waxes, or polar components like resins and
asphaltenes. Yes.
And this one doesn't have more or less
much of either. No.
No.
And therefore the grana should be better.
It's not a good candidate. And most oil spill chemists or people who are interested in how oil behaves at sea wouldn't say that you have actually used an emulsion, because this is more a slurry of
oil and water mixed.
Yeah. So because this doesn't form stable emulsions.
No, I cannot 100% remember if I wrote that, but I'm pretty sure that I wrote that it's an unstable emulsion in the thesis.
Yes. But we could go to some of your conclusions.
Sure.
Where you state about weathering.
Do you have a page number?
Yeah. Let's see. No, but you have in your. Let's see, maybe I have it. Yeah, page 136. Section 5.3, on the second sentence in the last paragraph.
At high heat fluxes, ignition was nearly instantaneous for all tested oils. That sentence?
No, yeah, and continue.
Independent of the weathering state of or volatile components present in the oil.
Yeah. And I think this independent of weathering state is probably stretching it a little bit too far. Since, or what do you think?
Well, the method, the ignitability was tested here is by putting a amount of heat on the oil and see if it can ignite by itself when having a spark over it. So it's rather different than the ignitability studies, for example, Janne did in that test, where you used the same ignition source for an amount of time and see if you can ignite it with that. So basically what I'm trying to say here is that as long as your ignition source is big enough to create a big fire, then it is independent of the weathering state. But how big that should be, of course, depends on the weathering state. So what I try to say here is not that weathered oils are easier to ignite or just as easy as non-weathered oils, but that the ignitability is a very strong function of how much heat you apply to that oil. And that is not so much as a question of this oil is ignitable or not, but how much heat do we need to ignite this oil?
Yeah, but for some oils, for instance, with the grane, when you have really high water content and really stable emulsions, even a high heat source can't put water into flames. So,
No.
So there is definitely a limit here, and weathering will be the main challenge.
Yeah, so what would be the idea of this type of data is that you have a heat source for an amount of time to basically break that emulsion and then ignite it. So it is indeed not the idea that if you have a very strong heat force for a very short period, so it does not say anything about how long you need to apply this heat source.
I see.
So because emulsions can break under heat stress, so to say, if you apply that heat source long enough, you'll basically end up with a non-emulsified oil layer on top of the emulsion that can then burn accordingly.
Yeah, but I don't think this heat source exists in real life. Sorry.
No, but that is also part of the conclusion of the thesis, where I write the ignition of oil slicks is not a question of yes or no, it can be ignited, but is there a heat source strong enough to ignite the oil?
Yeah.
And indeed, like for very heavy emulsified, stable emulsions, the answer might be no.
Yeah. But again, back to your objectives, that was to help or giving help to predicting if this oil slick could be ignited as a part of an oil spill response.
No, I wanted to predict the burning efficiency. So once it has been ignited...
No. Burning efficiency was in your presentation, but it's not...
Okay.
Burning efficiency is not mentioned here. Sorry. So here it's if the suitability of in-situ burning used in oil spill response. Yeah. So this is slightly different. Yeah. Okay. But let's move over to burning efficiency. Yeah, let's continue. On page 71, table 4.1. Yes. Now we have found the formula you have used for calculating burning efficiency. I'm still a little bit tricked about these numbers. Because, for instance, for Rebco in the last sentence, if I understand these numbers correctly, you start with 10 millimeter. Yeah. Then you burn it down to 1.6 millimeter. Okay. Then you have burned away 8.4 millimeter.
That would only be if the composition of the crude oil remains the same.
Okay. So this is not volume percent.
No, it's weight percent.
Okay. Yeah.
So in that equation where it said mass, the mass was indeed intended to be mass. Okay. So I collect the residue after the burn with hydrophobic absorption pads, and I know the amount of oil I add in weight, and then I weigh the residue on these pads, and that I use to calculate the burning efficiency.
But is the difference so large? Based on volume, this would be an efficiency of 84%, and you have calculated 52%. That's a quite huge difference. Could that be explained just by some density differences?
Well, that's what I meant with the changes in composition.
Yeah. That's the density.
Yeah, so the density increases, therefore the slick thickness becomes lower. Whether it could indeed account for all of this, I'm honestly not sure.
I doubt it.
I would have to...
But we won't go into...
Yeah.
You know, we are not going to start pressing the calculator now. Yeah. So, but that looked strange to me. Yes, if we approach to figure 415. 415. I don't have a page number, but
I should have it.
It's
here.
The,
Yeah.
Yes. What's the? You have mentioned it earlier, but what's the main difference between octanon, dodecan, and the two crude oils?
N-octane and dodecane are pure fuels,
Yep.
so they burn with the same same composition over time. So there is no change in composition where the components that burn in the oil during the fire get heavier, higher boiling points, lower burning rates. And on top of that, because this is small scale, the heat losses actually matter. And octane, for example, is so volatile that you can burn it down to a very, very thin oil slick, and then only then the heat losses start to matter. So the only reason we don't reach 100%, it's about 99%, is because at some point the water heat losses take over. But for these crude oils where there are much heavier components, because N-octane is really in the very, very light spectrum of what is in a crude oil, the heat losses take over much earlier, so you get these lower burning efficiencies. And although you can increase the slick thickness to make the heat losses matter later, so to say, the slick of the oil insulates the burning surface from the water layer. So the higher you make it, in theory, the longer it should take for the slick to be thin enough to reach the heat losses. And that might be indeed what we see here, where you make the slick thick enough to mitigate or to reduce the heat loss effect to its minimum, but then the incoming heat from such a small fire with heavy components is not enough to burn the next step. So that's why it's leveled off for the crude oils in this graph.
Because this is maybe a surprise to somebody that that we don't get a higher efficiency with a thicker oil layer.
That is exactly the point that this figure tried to show. Is like that there was in the state of the art document from 2013. That was one of the rule of thumbs. If you go higher in thickness, you will also go higher in burning efficiency. But that's one of the ideas I try to challenge in my thesis by saying that is not really how crude oils burn, because you also need not only to mitigate these heat losses, but also have sufficient energy coming in, and that does not increase when you increase the slick thickness. So yes, from this heat balance with incoming energy and outgoing energy, you take away the outgoing, but you do not improve on the incoming heat, so you level off, and apparently for these types of oils, about 60–70% is what you can maximum get in this diameter.
Yeah, but when you are burning on the surface, you have a certain flux of heat going down into the oil. So why is this heat flux dependent on the thickness?
It's not.
No, it's the same heat flux.
Yeah.
Yeah, but why do you then have a thicker residue? At flame out, when you start with 40, you will end up with a thicker residue.
So that is because
when you have the same heat flux down into the oil again.
No, the heat flux in the oil changes over time as well, because you start burning heavier components. They have higher boiling points, lower mass loss rates, lower flame height. the incoming heat, it depends on the burning rate and the flame height. So over time, the incoming heat decreases. So at some point, and that is not depending on how thick the oil is or how long the burn takes, but on how much of the oil has been burned. So apparently at 60-70% here, we reach a point where the heat flux created by those components is not enough to heat up the oil slick to burn the next set of components with a higher burning efficiency. So then it does not matter how thick you make your oil, that point will always be reached. And that is relative to the amount. So if you would increase your thickness, you still burn up to 70% because that's your cutoff for this change between having oil components that can still burn and oil components that will not burn anymore.
Yeah.
And it does not matter how thick you make your slick.
Yeah, I think that was a very good explanation. I had some problems grasping it from some of your text. Yes, on page 88, you use the term optimal thickness.
Yeah.
Yeah, that's not clear to me what you actually mean, or maybe also to some of the audience. Could you highlight and explain this to us?
Yeah, so then I actually go back to this graph. So the optimal thickness, what I explain predominantly in the paper that includes these results, is that there is this theory that you need to go higher in thickness to get higher burning efficiencies, but this data shows that that is not necessarily needed. But getting higher in thickness, as was shown with the Herder results, oil spreads out on water. So it takes effort to collect the oil and get it to a certain thickness. The thicker you want it to make, the more effort you need to put in thickening that oil, because otherwise it will just spread out again. So the optimal thickness is the thickness where your heat losses do not matter, or no, sorry, your heat losses are at its minimum relative to the thickness, but where increasing the thickness does not add extra burning efficiency. So in this case, if you have the middle screen, that would be at this point, because here we reach the maximum in the burning efficiency. It does not increase by going thicker, but by going thinner, we would lose burning efficiency. So that is what I mean with an optimal thickness, where you have your maximum burning efficiency for the least amount of effort, so to say. Do not put in more effort, more materials, more time, more money to thicken oil slicks above a thickness where it does not matter burning efficiency-wise.
But now it sounds in my ears that you are describing something operational.
Yes.
Yes.
The optimal thickness was from an operational point of view.
Yeah, but is this actually an effect you will see in real life with large diameter fires?
Well, in the thesis, I extrapolate these results, and by going into the question, okay, what would this mean for large-scale results, where we see that the burning rate is higher, so we have a higher heat flux, and we get less, or the heat losses are less significant. What would happen is that you reach this point of an optimal thickness earlier. Your point where you reach a stable plateau based on the slick thickness would come earlier because you add more heat, and your heat losses matter less. So what I tried to explain in the thesis is that for larger scale experiments, the optimal thickness would not be at 20 millimeters, what we see here, but would be much lower. It could be as low as 2-3 millimeters, which is about the ignitability thickness, which all comes down to the diameter matters, because once you ignite it, the thickness is irrelevant. We see that once you ignite a big oil spill, it will get to these high burning efficiencies. So that already indicates that if you ignite it, you are at the optimal thickness.
Yeah, so I think the concept of optimum thickness maybe isn't that relevant for a large...
No, exactly, and that is kind of what I try to show later on in the thesis, like this optimal thickness, or I studied the slick thickness and came to the conclusion, well, it doesn't really matter as long as you can ignite the oil.
Yep. Good. I have used my time and the questions. I have a few which I maybe return to later at the end. But thank you for very good answers and interesting discussion.
Yeah, thanks. And for correcting some mistakes in the thesis.
Thank you, Johan. And our next examiner is Professor of Physics.
Thanks. I hope you don't mind if I sit here.
No,
because
that's fine.
I don't have the privilege of running with my computer. You know, I have the thesis here, so I'm afraid losing my computer to the floor. And
That's fine. That's fine.
Well, thank you very much. I mean, it's been really an very, very interesting and nice presentation, and I've really enjoyed the discussion. I have to admit that he's taken some of my questions already, and in particular, I had also spotted the 1 minus in your efficiency, and but anyway, we can put that one aside because it's already taken care of. I kind of wanted to start with a little bit with your conclusion. I mean, you made a very strong statement.
Yes.
About ignitability, and if you can go back, you know, to the slide of the conclusion, and I kind of want to start there and trying to understand really what you mean.
Is it this one?
Yes. So you said ignitability of a spilled oil slick is therefore the most important parameter that determines if in-situ burning will be a suitable oil spill response method.
Yeah.
So can you go back? I mean, you know, both in your thesis and there, you went really, really fast through that statement.
Yeah.
And I'm trying to really understand where does it stem from, and why do you really think that that is a correct statement?
I'll explain it based on this figure. So what I try to show is if you have in-situ burning, and you, as a decision maker, you have to make the decision, do I want to apply in-situ burning to this oil spill? Then from that point of view, there is no longer a question of what will the burning efficiency be. Because you have a large oil spill, the diameter will be large, so if you manage to get that fire burning, you remove most of the oil, which is, I would say, the key part of in-situ burning, removing that oil from the water. So if the burning efficiency becomes inherent to the scale, you can leave that out of the equation whether or not you want to try in-situ burning. And then it mainly comes down to, okay, can we ignite the oil? Can we put effort in trying to see if this oil is ignitable? If we get it to ignite and have flame spread over the fuel surface, then we will burn it. So, of course, in this statement is from a operational point of view, looking at how much oil can we remove from the water. It does not take into account environmental effects, like what will the smoke plume do in this environment. So whether it will be a suitable response method is not taking into an environmental context here. Purely from a practical point of view, can you ignite the oil? If the answer is yes, then we will get high burning efficiencies, and therefore the statement is that it is an effective response spill method.
Okay, so if that's the case, then go to your ignition delay time plots.
This one or this one?
Either go the one before because it's more physical. Okay. So I have no doubt that you can ignite everything.
No, but that is exactly what Per-Johan and I discussed about. If your heat flux is strong enough to ignite a certain source,
but
you can ignite it.
8 kilowatts per meter square. I mean, I see all your crude oils, and you ignite every single one of them with 8 kilowatts per meter square or more. And I can produce a heat source with 8 kilowatts per meter square with no problem at all.
But that's inside a laboratory.
No, it's everywhere, because it is a fundamental property of the material. The only thing that changes is the convective heat transfer coefficient, and maybe if you're blowing a very high wind where you take the square root to get the Reynolds number and the convective heat transfer coefficient, you will get maybe to 12. Okay. I can produce 100 kilowatts per meter square if I wanted with an appropriate heat source, and I can do it in the middle of the Arctic if I wanted. Mm-hmm. That's not a challenge. We know we can do that. So then where is the ignitability?
That's a very good point.
That I expect you to answer.
Yeah. If you give me a second to think about that.
Let's take a step back, okay? So when you start describing this thing, you made a statement saying we wanted to ignite.
Yeah.
And then it has to spread.
Yeah.
Okay? And I think that's where, I guess, the confusion stems a little bit. When you came up to that conclusion was based on a series of experiments that you did with the ice.
Yeah.
Okay? And,
yes.
To some extent, okay? So what was the observation there? What was the fundamental observation that you made?
Well, the ignitability, the ignition was actually rather very difficult from a practical point of view, because what we used during the ignition is either a small hand torch, but when trying to ignite the oil, we would have so much force coming out of the, or such high flow from the torch that you would blow the oil away if it's not big enough to contain itself. Or we would use ignition gel, which is a volatile component, volatile gel that easily burns. But if I would pour that on the oil and try to ignite it, the gel would burn, but it would just push away small oil slicks and then not burn any of the crude oil. It would just burn the ignition gel. So it was not so much a problem as getting the right heat flux on that oil surface, but to get a ignition source that would get the oil, keep the oil together and still be able to heat up that oil on the spot instead of dispersing it while trying to ignite it.
Yeah, so effectively what you're doing is what you're telling me is that it is not about actually being able to ignite the oil per se in itself. It is a capacity that you have given the conditions.
Yes.
For that flame to actually persist and persist to a level that it can start covering all the
that
area.
You get flame spread. And I believe that in my thesis also mentioned that if you get ignition and spreading of the flame over the fuel surface, once you have that fully developed fire developed, then you will get those high burning efficiencies.
Okay, so then let's just go back then to the principle. So basically, it is really not ignition per se. It is actually the capacity for the flame to spread. Now, I can accept the ignitability because I see spread as a sequence of ignitions.
Yeah.
Okay, but the source is what changes. So if I can actually have a spot, okay, and I can put a cone heater around it, even if I'm in the field, okay, I can put a cone heater around it, flash it with 100 kilowatts per meter squared, okay, and get a vacuum that is pumping out the mixed fuel and oxidizer, and I ignite the gas, I will get a flame.
Yeah.
Okay, there's no question that I can actually ignite.
Yes.
Okay, the problem is that if I have to repeat that all over the oil spill.
Yeah, your flame needs to, because yes,
your flame needs to be
big enough and long enough heating that surface to actually spread to the
so
rest of the fuel.
The flame needs to be capable of constantly producing that heat flux.
Because indeed the heat flux is very low, but then the ignition time is very high, so it takes a longer time to spread to the next step, so to say, of the next ignition. And if your flame by that time has already died out, then you will never get that flame spread. And that's a bit of a problem with the ignition gel.
Okay, this is where it becomes interesting, okay, because now you keep adding all this other terminology. We haven't moved past ignition, and now you have burnout. Mm-hmm. And you're talking about all these other things that are happening. So we can accept that ignitability does have a problem. It is an important issue. because effectively is what you really need to be able to continue to spread. So ignitability is valuable only as a function or as a measure of your capacity to spread the flame.
Yeah.
It is not the phenomena of ignition
No.
that matters, but
no.
it is the capacity that you have to have this sequence of ignitions that represent flame spread.
Yeah,
Okay.
and my use of the word ignitability is maybe a bit too liberal in that sense, where I also include the practical applications of getting the oil to ignite and then spread the flame, where flame spread is not necessarily incorporated in successful ignition.
Okay, so let's just, then we understand what
Yeah.
we're talking about now. So effectively, I'm not objecting to the word ignitability in
But
the sense that
needs
it's
to-
associated to spread.
Yeah, it needs to add a bit more on it.
Yeah, so then you say, well, okay, so then spread differs from forced or external ignition in that the flame is actually producing the heat source
Yes.
that enables you to reach this 10, 20, 30 kilowatts that
Yeah.
you need for this. Now, obviously, the stronger your flame is, the higher your heat flux is going to be,
Yes.
the shorter your ignition delay time, and if your ignition delay time is short enough, then you will be able to spread before you burn out.
Yeah.
Okay? And that seems to be the threshold, no?
Yeah, and that is what is part of the difficulty when igniting emulsions, because there you not need to just heat up the fuel to its flash point. So you have the flame here, and the next part you want to ignite and spread the flame over. So you're not heating just the fuel to its flash point so you can have flame propagation, but you first need to break the emulsion, put a lot of heat in that to separate to separate the water and the oil, either by evaporating some of the water or by breaking the emulsion another way, and create a fuel layer that consists just of your oil on top of the main bulk of the emulsion, and then heat that one up. So so your ignition delay time increases when you start emulsifying your oil.
Yeah, and I wouldn't disagree at all. Although you're adding just another level of complexity to it. We haven't moved beyond the basic one. So we're talking about the fuel
Yeah.
and the balance between your capacity to deliver the heat flux for a period of time corresponding to the ignition delay time, as opposed to your capacity to maintain burning until burnout.
Yeah.
Okay, whatever that situation is. Okay, so now that we understand what you really mean about ignitability, okay, how do you quantify this balance?
Well, you could use the apparatus that you have used with WU, where you looked at the flame propagation apparatus, where you have your fuel service and then a heat source that has an angle to it to see up to how far you get flame spread, so to see what is the minimum heat flux you need for the flame spread. That's one way of quantifying it. But that would, I'm not sure in what sense you would be able to take into account all the practical problems with igniting such a fuel or getting flame spread on a fuel in field applications where you could also have waves and wind on your water surface.
Yeah, but I completely agree with what you're saying. But once again, I am the kind of person that has a very linear and simple brain, so I build blocks. Okay, so before I get waves and emulsions and all these complicated things,
you look at
I want to understand, laminar flat surfaces with a thin layer of homogeneous oil. If it was single component, it would be ideal, but I do agree with you that the multi-component nature of it is fundamental.
Yeah.
Okay, and but when we developed that hardware, the reason why we developed it was effectively what you just described. We were trying to see how much do you need to supplement the flame, before the flame is incapable, of igniting. Okay. And I agree with you that obviously there's enormous limitations, on that hardware. So let's just put the hardware of that we developed on the side. But I'm interested because eventually you're right that you have to bring all these measurements or tests or whatever. You have to bring them to a level where you've taken into account all the variables of the practical problem. So idealized scenarios only bring us this far.
Yeah.
Okay? And you are attempting to putting yourself in a space where you have a piece of hardware that enables you to introduce other factors into the problem. So given that that's the objective, then once again I ask the same question. It's like, how do you move to the next step? So how do you actually bring what you're doing to the point where you can actually quantify that balance between what the flame can provide and what you need to ignite? Because in principle, that goes back to your conclusion. That's what you want.
Yeah. Well, you somehow need to find. Are we still talking the ideal situation or the more practical, where you take into account all of the things?
Well, you've created a hardware that enables you
Yeah.
to address some of the practical aspects. You
So
know, I had a hardware that was way too idealized and did not allow any of these things. Okay, but the objective of what I was doing and the objective of what you were doing, now that we have agreed, is the same.
It's the same. So in the hardware I have, what I would propose to try is to have ignition and in one of the corners, or well, I don't have a corner in a circle, but at one spot, and set up the lamps in such a way that there is a heat flux gradient, an external heat flux gradient around your oil slick to mimic this hardware where you have just a panel like this in here. And I'm sure that with the 4 lamps, I should be able to create such a gradient over my fuel surface, then ignite it where the external heat flux from these infrared heaters is the highest, and see up to where I can get ignition. Mm-hmm. Because in that hardware, I can have the water cooling it from below, and I could potentially set up some sort of wave mechanism so I can create waves in that water basin, and a van or two to create some sort of wind flow could also be used to get more and more to realistic conditions. And if we would scale it up a bit, because this is maybe a bit limiting in size with the 16 centimeters, you could also start incorporating ice in it. But for that, I would use a larger basin than just 1 square meter. Because ice, the interaction, that was also why I didn't scale full herding. The interaction between ice and oil changes really when you start scaling ice flows, because the area to size doesn't really scale as nicely to these very small scales. So then I would go into a bit higher scales and have larger oil spills where we can ignite it on one point, have all these conditions, and with external heat fluxes at different points of the fuel, see how far does it propagate, so what kind of starting fire, or is this oil capable of producing a fire that can fully propagate the flame over the full surface, or does it die out at some point, and what is then the additional heat flux that would have been needed. So then you could categorize, so to say, crude oils or weathered oils on the additional heat flux that would be needed to get full flame propagation after initial ignition.
Okay, and I mean, I agree. I mean, that's more or less, I think, in concept, what I think your hardware enables you to do, because you can create the same conditions that I had with a single lamp with all the 4 that you have to create a heat flux distribution around the thing. Now, then that brings back to the question of how big will you be your ignition point?
Yeah, that is, you need to have, in this small scale, I would say that you cannot really do it, because if you have an ignition point of only a few centimeters, then your flame is not even turbulent yet. So you're looking at very different flame conditions for your ignition point than you would ever have when doing in-situ burning in the field. Mm-hmm. So you would definitely need to scale it up, scale up the size to have more oil to spread over, so you can get actually a somewhat representative flame to start and have that one propagate over the fuel surface. Because if you go too low, your flame is not representable in any way, as we see in the diameter and burning rate graph. So that's why I say I would like to go bigger, to be able to go maybe 10, 20, 30 centimeters and really have a nice turbulent flame, or transition turbulent, technically, to get that ignition started. Because that is also, I would say, the amounts of or the ignition size that you would get when you use ignition gel. You cannot pour hundreds of liters of ignition gel on top of your oil and hope that it then spreads out. What I've seen from the use of ignition gel is that you use an amount that corresponds to 10, 20, 30, 40, 50 centimeters in diameter. So that would then be my ignition source. So I would also take something like an ignition gel as ignition source to get a bit more representative than trying to ignite the oil with just a hand torch on the spot.
And I would agree. I mean, and I think that that was the purpose of the ignition gel. So they were trying to create a sizable enough ignition source that became, I guess, representative of a robust, optically thick flame that can actually produce enough heat flux. If you look at the thickness of the flame, as it becomes more and more turbulent, then it becomes optically thick. And then it reaches a peak of the heat flux that is delivering.
Yeah.
So if you make the flame big enough, then you attain your maximum heat flux. Yeah. And that's where you want to be. And that's what they were trying to do with the gels. Find the minimum size that brings you to that level where you are optimizing your heat transfer from the flame, you know, to the oil. But as you observe, the moment that you put the gels, you create a whole set of other problems.
Yeah, well, on the small slicks, actually, on the larger slick we tested, I had the feeling, and I didn't test this, but this is just visual observation, is that when you add the gel to a small oil slick, the gel spreads out as well, and there is simply not enough bulk of oil around it to withstand that spreading pressure of the gel, to have it, instead of pushing it away, spread over the oil. So when we use that large ignition that large scale, this one actually, here that fire was started from ignition gel. So here the ignition gel spread over over the oil and then resulted in ignition, flame propagation over the crude oil, and that resulted in the fully developed fire we saw in the video.
Yeah. So I mean, don't you think that it would be a much more intelligent way of igniting, other than throwing gels, to have actually an ignition device that was based on radiative heat, for example, that managed to ignite a significant sort of diameter of the crude oil directly without having to run into all these messes that comes from the combination of different fuels?
In theory, I would say yes. In practice, I think that, well, the way they ignite, or what they have been testing to ignite spills with after hurting, is using a heli torch. So they have a helicopter that basically spreads out napalm over the oil slick to ignite it. Because getting a device in the Arctic over a spill with ice-infested water, then we're looking at making the logistics more and more complicated, which was one of the benefits of in-situ burning, of having or having relatively simple logistics. So I think it will be really a balance between what are we capable of bringing to an oil spill location and what is the optimal equipment to use in ideal situations.
Yeah, I mean, you can take that approach and say that, you know, this is a simple way of doing it, but I could also see it as just simply a dumb brute force.
Yeah.
I mean, throwing napalm, give me a break. You know, that's a little bit too much. I mean, why can't you just put a radiative device on a drone and just fly it over the thing?
I don't know.
Yeah, I mean, I think if you really understand the problem conceptually, you know, it is clear that having a radiative device is a much more effective way of doing it than putting anything on that perturbs the oil slick. From a practical perspective, I agree with you that there's many, many, many considerations. But I think that the fundamental aspects of it have been, there's a tendency to forget the fundamental aspects.
Definitely.
And basically use intuition to try to achieve something that in reality should be done with brains and not with intuition. So, so now we're in agreement. So now we know what ignition is. Let's now move to burning efficiency.
Sure.
So what is then the fundamental physical parameter that controls burning efficiency?
I would say it's the heat balance. The amount of heat that is available for the bulk of the oil to be heated up during the burning to evaporate all these heavy components that are needed to get the high burning efficiencies.
Well, now you've talked about all, okay? But that's not what happens. I mean, eventually, what happens is that you have a residue, and the residue will always be there, and it might be 1% or 90%, but that's what determines your burning efficiency. So what is the physical process that effectively lands you in that position of the burning efficiency? What happens at the end of your test?
Well, you get flame extinction.
Okay, so now we are using the right terminology. So then what is the physical process that effectively controls burning efficiency?
The amount of gases that vaporize from your fuel and make sure you have a self-sustaining flame.
Okay, so why are you trying to avoid using the word extinction? The same way we had ignition, we had flame spread. Now we're talking about extinction.
Yeah.
Is that the physical process that controls the end and what determines what your residue?
Yes. After extinction, your fire is done.
Exactly. So then you get left over.
Okay, yeah.
So if you delay extinction to 99.99% of your fuel, that basically means that you have a burning efficiency of 0.01. Sorry, of 99.99.
Yes.
Sorry, I forgot the one again. Yeah.
Yes.
Do we agree?
Yeah,
Do
definitely.
we agree? So then why in your thesis the word extinction doesn't appear?
I don't know. Maybe, like you said, why do you try to avoid it? I put it in different terms because...
No, but there's no different terms. The physical process is flame extinction.
Yes, but I cannot... The reason I don't use that word is because flame extinction does not tell me anything on why the flame extincts.
Yes, it does. Because what is the physical parameter that controls flame extinction?
The amount of volatile...
exactly, it's a critical mass burning rate.
Yeah, the mass burning rate.
So why does your thesis doesn't include the critical mass burning rate?
I don't know, because I didn't think about that.
Yeah, but it does. Everything that you work on goes tiptoes around it.
It does not specifically mention that term.
Yeah, but everything. I mean, can you go to your the plot that you have of burning efficiency as a function of external heat flux in the cone calorimeter tests?
Yeah, sure. This one?
Yes. So what is happening there? Can you explain to me that plot? What does the external heat flux do to the burning efficiency?
Well, by adding the external heat flux, we basically mimic the higher burning rate in large-scale fires. So we get more energy to the heat, to the oil, while the heat losses...
Let's forget about the large-scale and everything. You get more energy to the oil.
Yeah, while the heat losses remain the same because, yes, we have the same amount of cooling from the water. It's the same temperature that flows through it with the same flow. So we add more energy to that oil. So therefore we are capable of evaporating components longer. So we can evaporate components with a higher boiling point, so which means that we can burn for longer. So basically we delay flame extinction.
Exactly. So when you look at your burning rate, you have a decaying burning rate.
Yes.
Okay, because your components are getting bigger and bigger, so it's harder to get them out.
Yes, exactly.
Your layer is getting thinner and thinner, so you have bigger losses going to the bottom. So eventually what you get is a mass burning rate that hits that threshold of the critical burning rate.
Yeah.
Okay, once you reach the threshold of the critical burning rate, then eventually the flame extinguishes.
Yes.
Okay? So the moment that you add heat, you delay because you push your curve a little bit up.
Yeah.
So you're crossing now later. So then you have a higher burning efficiency.
Yes.
And then you add more heat, you cross later.
Exactly.
Okay? And that's exactly what you see in that plot. So effectively, I could have explained that plot by saying I'm delaying extinction.
Yes.
Okay? And I could have used literature burning rates because the gas phase flame is always the same. It doesn't matter what the hydrocarbon is. okay, then I could have used the 4 grams per square meter that is a standard number, and basically look if effectively I can correlate that value. And all that data there could have been replotted against the critical burning rate.
Yeah. Good idea.
Yeah. So why did you ignore all that?
Because I didn't know about it. That is the simplest.
I'll leave it to you to decide if that's a good excuse or not. Okay.
That is not. I was not saying it was a good excuse.
Yeah, but I think that if you know, I generally, when you deal with extremely complex problems that have a lot of parameters that play with the problem, what you do is exactly what you did, and it's the right thing, which is explore all the parameters. So you're walking and looking, oh, this affects this, this affects this, this affects this, and this affects this. And sometimes when we do that, because there's so many parameters, you know, we forget the obvious, you know, which is what is the one thing that links all these parameters.
Yeah.
And I think here we need to have the processes clear. You have ignition, you have flame spread, you have burning rate, and you have extinction.
Yeah.
And extinction is what determines the burning efficiency. So in principle, it would be great for whoever follows up your work. So in the prospects for the future work is rephrase, you know, the enormous amount of resources the results that you have, you know, rephrase them in a way such that actually address what the fundamental physical process that you're trying to describe.
And
so anyway, so I mean, I think that is, you know, I guess in many ways sort of the main, you know, question that I had is, in your mind, I think it would be good to switch a little bit the terminology in a way such that it actually reflects the physical processes that are going. It wouldn't change at all the conclusions, because it is an issue of ignition. It wouldn't change at all the presentation, because effectively you're going through all the parameters that affect extinction. You're just avoiding mentioning the elephant in the room. Okay? So then I have a couple of, you know, of little things. I mean, you put the equation that you developed of the energy balance. Can you put it in there?
This one, right?
I think slide 19, yeah. Yeah, so I think one of the things that is really interesting in there is, I mean, obviously the equation is correct. So you have this, if sort of chi is the Q net divided by Q, and then what you get on top is absolutely correct, is the gasification energy plus the losses divided by the heat generated by the combustion process. Okay, so all that is fine, and the breakdown is correct. So your conclusion is that increasing the diameter increases the available energy to the heat to the oil slick.
Yeah.
You know, which, yes, I mean, there's many reasons where you can argue that that is the case, and obviously the second term in red clearly defines that, because your burning rate reaches a maximum, so the whole thing becomes the smallest possible number. But that all requires that the value of chi is a constant.
Yes.
Okay, so do you have anything that actually demonstrates that that is the case? Because physically speaking, it is the net feedback. And if you take some of the large-scale tests, you know, you get the soot blockage and you get all these other phenomena. So what do you think about that value of chi?
This was I would say, difficult part for me to look into, because when I made this derivation, this is very much theoretical, because chi s is not a constant. It depends. I'll just have another slide. Yeah, so in this slide, we have the B number, or Spalding number, which shows is equal to 1 over chi s. And it's assumed in a lot of literature that this number is constant. The Spalding number for a certain fuel is constant, so therefore chi s is constant. But for crude oils, this does not apply, because the term, where is it? the surface temperature minus the ambient temperature is not constant. For pure fuels, we would have that the surface temperature is constant, like we see for N-octane, for example, and your ambient temperature is also constant. And then we can assume the Spalding number is constant. But because this term changes as a function of time, as we saw in the heat loss or the temperature plot, where the temperature between the surface and the water-oil interface increases over time, your B number would change. So therefore, your Chi-S will also change. So this was very much a theoretical approach to show there's something going on with the diameter that has an effect on the heat losses. Mm-hmm. But in absolute terms, it's very difficult to say that this equation is 100% true, because furthermore, it assumes that your heat of combustion is not affected by the combustion efficiency whatsoever, and that your combustion efficiency is 1 throughout the whole burning. Yep. And looking at the plume of a crude oil fire, the combustion efficiency is clearly not 1. And that might also change as a function of time, considering the ratio of hydrogen to carbon in hydrocarbons goes more into favor of carbon when increasing in molecular weight. You have methane is CH4, and that's the only hydrocarbon that has 4 hydrogen to 1 carbon ratio. And because carbon is the compound that creates soot, it's likely that you add more soot relative to other gases when you burn heavier components. So there are so many things in this equation that in reality are not constant. And I had looked at the derivation that Hammonds and his co-workers made, and I had questions myself, like, how can they do this? Why do they state that these things are constant? But from a theoretical point of view, to grasp the concepts of what is going on, it helps to explain it in a mathematical way and give it a bit more a tangible way of showing it, rather than just saying it will increase and just use terminology.
Yeah, no, and I mean, I think that that's the question, the answer that I was expecting. I think if you go back to the slide that you put of the B number, yeah, so that definition of the B number is a purely diffusive definition of the B number, and effectively is an ideal ceiling value. So effectively, that gives you the maximum possible exchange, because you have complete heat of combustion, okay, and effectively you're only bringing constant ambient temperature to the surface temperature. So effectively, you have no losses involved in there, and you have no combustion efficiency, and then you don't have any other forms of heat transfer other than purely a diffusive form of heat transfer. And I think you should think a little bit also of the same type of nuances when you cite the DLV method of law, because while conceptually it does describe this process of, I don't know what to call it, the distillation or whatever, that you're getting the different components out, it is defined as a purely diffusive approach associated purely to droplet combustion. Now, clearly when you have a problem like the one that you have, there's a lot more variables that are going to play in there, because you don't have a diffusive heat exchange between the flame and the fuel. If you have a perfectly spherical droplet, okay, and you have a sphere in here, and heat transfer is only through diffusion, then you get the D-squared law, and then you get the DLV, and then you get the Spalding B number, and you get all these things make sense. But when you get a problem where you have heat losses, complex radiative exchange, plus convective, plus diffusive heat exchange, and all that stuff, then all of a sudden this just becomes a way to explain, the physics, and not necessarily something that that can be used in a sort of pseudo-quantitative way.
Yeah, and well, I also tried to get some sort of quantitative estimate, but it was very difficult to get any sort of estimates of what would these heat losses be, and that's why I ended with this equation. Like I was kind of stuck there. Like, this I can show, assuming all these things, but they're not the case for my scenario.
Yeah, absolutely. But I think as a way to explain the physics, it makes a lot of sense. So, I mean, one last thing, and it's just, this is purely a curiosity. So if you go to slide 25, sorry. The middle one. So basically what you have is water in the bottom, and you have a layer, a barrier, and then you have oil on top.
Yes.
And you get this increase in burning rate.
Yes.
that happens at the end.
Well, for the middle one, it does not happen in the end.
Well, it happens at some point.
Yes, yeah,
At some
but it
point.
just...
Now, does that coincide with the fact that, that you're creating film boiling? Because you have water underneath, and there's massive heat transfer going on, and at some point, you might create film boiling on the water, which is basically a layer of steam that reduces the thermal conductivity. So you're basically insulating, and that's what's you're minimizing your heat losses all of a sudden, and you create enhanced burning, because it goes from being low to, it's like a step function. And so it's nothing that is increasing or anything like that. It's just a curiosity.
For the video I show here,
steam?
yes, but only at heat fluxes of, I think, 40 and 50 kilowatts per square meter from the cone. So I think it's even only 50, and there you even hear it. There's steam coming out of the water outlet rather than water. But at the other ones, the water heats up to 60, 70 degrees, and so we get clearly water and no steam going out of the tube. Whether there's steam inside the holder, that I cannot test, but considering the temperature of the water for lower heat fluxes like 5 and 10 kilowatts per square meter, where we also see this phenomenon of the boil over with just the crude oil, does not go above 45, 50 degrees, I would say there's no steam inside that cone holder. So that would only happen at the highest heat fluxes.
Okay. 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 That's it. Thank you so much.
Thank you. Final thesis examinator. Marie Gelderen.
Yeah, I'll get up. Yes, Lawrence, so compared to these two, I'm not paid, to be just here today to ask them in questions. This is part of my job at the department. So I will try to be nice because I'm a nice person, but also because I will meet you on Monday. I would like you to still say hello to me. So I think it's a very interesting piece of work, and it's a very nice presentation, I think. And I like the visuals with the videos. It shows very clearly to me and also to the audience, what you've been doing in the lab. And I think that as a PhD student or through your study, you show that you're not afraid of, doing what you have to do in order to reach your results. You do like small scale experiments, you do intermediate scale experiments, you do some modeling and fundamental studies. And I think that's very good for a PhD student. Some tend to want just to stay in the lab, or some just want to do the modeling. I think this it's a good example of, mixing these things.
Thank you.
Yeah. And I'm sure that you would like to do a large scale burning if you could.
Yes.
We'll get back to that later. Also, if we look at your thesis in itself on the structure, I was a bit surprised actually when I received your thesis, because you've written some and published some papers already, and they weren't a part of your thesis. And I mean, there could be different reasons for that, but we agreed that you've written this kind of old-fashioned thesis, which is very nice for the opponents, because everything is, in a nice order. But I wonder, how much time could you have saved some time if you had included the papers that you could have, worked on the experiments?
It depends on how I would incorporate the papers. If I would just say, this is paper 1, it's a chapter, read it and don't do anything, then yes. But if I wanted any sort of flow in my thesis, any sort of story, then I would still have to write around those papers and introduce them. Why do I do this research? And how does that how did it come about, and what does it follow up to? And also the papers I published were not really in the same order as I present the results in the thesis, because to me the first thing that I wanted to show was the vaporization order. The way it's in the paper is maybe more complex than I could write it now in the thesis. And I used a lot of text from the papers to put in the thesis. So I don't think actually that choosing a monograph style thesis costed me a lot of time. It also gave me the opportunity to, in a nice way, integrate some extra things that they did not include in the paper. Like, for example, the figure with the intermediate scale herding experiments. I could show that now in the thesis. Whereas if I just have the paper, and then your paper is a standalone thing, and then you have on this standalone thing an appendix with all the extra information, and you have to constantly switch between those things. And the other thing I don't like about having the papers as their individual chapters is basically you're reading the same introduction to the problem over and over again. It's basically blah, 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 bunch of references, and then you get to the methodology and what you actually did. The introduction in the papers is not enough as a standalone introduction, so I need to write an introduction anyway. So I was not really sure how I would have structured it with the thesis. With papers, I would have put them in an appendix, I suppose, and refer to them a lot. But then you have to browse, and I don't know how much time I then would actually save. And I would say that I shortened the writing time to 2 months, during which I also still did experiments, these cone experiments, and wrote a conference paper. So getting even more time for the experiments, I think, would have been somewhat unrealistic.
Mm-hmm. Well, thank you. And I think, your explanation here shows that, the reason why you also did this, is because, this is a very good PhD study. You have the overview and you have the capability of writing the thesis in this way. A lot of other students, they would have gone for the easy way. So I think, that's also...
Well, I have to give credit where credit is due, because Grunde kind of made me write it monograph style, where I was like, I don't know really what I want, pick monograph, okay.
Yeah, I don't disagree with you. I was just a bit surprised. Most PhD students like to brag about their published papers.
Well, I included them in one of the first pages, said this is what is published.
Yes, yeah.
So
yeah. Yes, I would like to ask you to, one of the first figures where you show the 3 different response methods. Here, yes. So, you have an oil spill, which is, from an environmental point of view, a bad thing.
Yes.
And then you want to do something. Could you explain a bit the advantages and disadvantages of the in-situ burning compared to the other 2?
So the mechanical recovery is the main oil spill response method that most countries, both Arctic and non-Arctic, have in their policies that should be used in case of an oil spill. And that is mainly because it actually cleans the oil from the whole water environment at that point. It picks up the oil and stores it in any sort of container for later disposal. That is the main downside of mechanical recovery, because it is usually done through skimmers, which have a conveyor belt that rolls over the water surface to pick up oil and should not pick up as much water, but they do. So you get very large amounts of a oil-water slurry that you need to get rid of somehow. And I know from colleagues at WPI that they're working on ways to efficiently burn that, so you're basically doing in-situ burning still, but later in a more controlled environment, where you can deal with the gases in a better way. Dispersants have the highest cleanup capacity, where cleaning means removing it from the oil surface. During oil spill response, the main thing everybody aims for is get the oil from the water. Whether it goes in the air, in the water, or somewhere else, that is not as much of a concern, as long as it doesn't hit shorelines and interact with a lot of animals that interact with the air-water interface, so to say, like mammals and birds. So dispersants put the oil in the water column, and the idea is that by making this oil into very tiny micro droplets, that they're more available for bacteria that eat these and degrade these oil droplets. Whether that is the case, I will not go too much in detail about, but there is debate about whether this is indeed effective. And if you sometimes read studies about the Deepwater Horizon spill where they used dispersants a lot, it's like, oh, the dispersants are worse than the actual oil, or we should not have used dispersants because dispersed oil is more toxic than naturally dispersed oil. So there is still a debate on, are dispersants good for the environment? And then with in-situ burning, the environmental side is rather obvious from the big smoke plume that has to go somewhere. And there's anecdotal evidence that the smoke plume doesn't really dissipate on ice, and that has been published in some documents, but it's only anecdotal evidence. There have been no studies in the Arctic on what such a smoke plume would have on an effect of ice. So there have been studies that look into the smoke plume, into the toxicity and what does it, but not in an Arctic context where you can have ice that if smoke deposits on it, you reduce the amount of reflection it has from sun so that it heats up faster and it starts melting faster, which is the same problem as black carbon from ships. There is this concept, the NEBA, I explained it briefly in my thesis, which is the net environmental benefit analysis, which basically asks a question in twofold, like, should we do something? And if we do something, what? So this assumes that we need to do something, and then you need to pick the best response method, but it might be the easiest to just let the oil be and say, well, it's bad, but whatever we're going to do is not going to make it any better.
Yeah, thanks. And you mentioned the NEBA.
Yeah.
So what does it contain? What are the steps in a NEBA? What do you need to know?
Well, for a NEBA, you need to be able to know what are the damages the oil will do right now when you don't do anything. Then you need to know what is the damage of your response method if you would do it. It needs to be, it is not a, it's not a document that is binding. A lot of the, for example, actually Denmark states that if you want to do in-situ burning or dispersants during an oil spill, the responsible party must make a NEBA to show that it is indeed beneficial for the environment to use one of these response methods. The exact steps of the decision process, I don't know. I focused on the concept of what it is. It's comparing no action versus an action and what action should it be then. And it depends purely on the environmental side.
Yeah, and it's quite obvious, as you say, from the in-situ burning. It's very visual.
Yes, and that is also what, if I explain my work to people what I do, then one of the first comments you get, but what about the smoke and those things? Because it's so visual. And that is, well, if I explain it to people who have a bit more, who think a little bit further, and you talk about dispersants, I was like, yeah, but you just put it in the water. You don't clean it. Mm-hmm. And then it becomes very difficult to say, yeah, but that's the purpose. That is what we call cleaning of oil spills, because it doesn't get any better. It's visual for in-situ burning, but that does not mean that it's actually worse for the environment. Yeah. It's very bad for the public perception. Mm-hmm. It is only allowed by 2 countries, I believe, in the Arctic region, and I think Denmark you can do it if you make a NEBA that shows it. Mm-hmm. And also for dispersants, it's still very hesitant to use it. Only the US is really like, yay, dispersants. So it focuses a lot on the mechanical recovery, but as you can see, the problem with mechanical recovery is you can't actually recover that much of an oil spill. Of course, it has to be said here that Deepwater Horizon was an extremely large spill compared to a regular oil spill. But still, you cannot clean up all the oil using either one of these methods.
Yeah, and you've looked a little bit into, looking at the environmental properties of the residues.
Yeah.
It's on some of the last pages, 128, 129. And was these tests, were they made with the new setup?
Do you mean this? No, this is the gases.
Yeah, it's just smoke analysis tests at the water
Yeah.
fraction and residue
Yes,
composition.
but not with the heating lamps.
Okay.
So those heating lamps sadly did not arrive in time to do those experiments. I was promised a certain delivery time, and that was not really taken into account with my experiments, that if they go over it, I would have a problem. But so these experiments featured the cooling of the water, so we did not go into boil over, and I captured the gases, but there was no external radiation. So basically what these show is the toxicity up to a certain burning efficiency. Because that the adding that heat flux would not change the chemical composition of the components that were burned at that point, ideally. Maybe because of the extra heat, the combustion is affected as well. But the only idea of adding that heat is by being able to burn more components and not the same ones we already burn in a different way, to put it like that.
So, well, you say that it should be, tested further in this setup, and that's what I believe that you would like to do in this new setup, sample the gas and everything. And what do you expect from these? What do you expect them to show? Because you've shown figure of 436. You have the combustion products in the gas from this one test. And this is, as I understand, is from 30 seconds of sampling.
Yes.
And then you also have the problem with you have the water.
Yeah. This was very much a prototype, but I wanted to still include it in the thesis to demonstrate the new setup, because that was one of the things that I found very important during my work. Like, hey, I slowly evaluate or improve this setup to a point where I say, okay, now I can better mimic large-scale experiments. But there were a lot of children's diseases still going on with this. So what I would hope to see is that you can get some sort of measure as a function of the burning efficiency and therefore burning time. So if you have at the start of the burn, what kind of components do you see? At the end of the burn, what do you burn then? And then looking, for example, at PAHs, polycyclic aromatic hydrocarbons, that are considered to be the most toxic things that come out of such a smoke plume. But it's also to get maybe a better understanding of the chemical balance of an oil spill. Because we burn the oil from the water surface, and what we collect and say whether it's effective or not is only what is left on the water. And then we say, oh, we burned 90%. But if 20% of the oil actually sank during the burning somehow, either after extinction or during the burning, we didn't burn that. It just went to the water surface or went into the water column. So what I hope to see is if I can get some sort of idea or grasp of where does most of the hydrocarbons from this oil go. Do they indeed go into the gases? Do they go into soot material, solid material? Or do they go into the water layer? And then breaching that out to toxicity, we work together. This work was done together with the Copenhagen University Chemical Analytical Department over there. And they would be more responsible for what is toxic and how much.
Into the quantification.
Yeah.
Are you planning more experiments here?
Yes, definitely. I'm still in contact with the Copenhagen University. The lamps are now finally there. So the setup is about ready to be used. I need to calibrate it, see what kind of heat fluxes can I make, with these infrared heaters. And then the next step is to, well, remove the water, as you can see here, because basically I drowned my samples in water and couldn't see anything. So to remove the water in one way or another, I have the heating tape. We will see if that works. And where I had already a meeting with the professor at the Copenhagen University I work with, and say, okay, what kind of steps do we need to go through? Do we indeed get gases? Like my gas inlet is currently a first prototype, and I don't know how much does it get a representative sample of the burning gases. So we will have to build that up step by step, especially the smoke capturing. That is the most complicated part of the setup because it has not been done as far as I know. I've looked for it but couldn't find anything remotely similar that studies smoke plume gases from an actual fire and not inside a compartment or so. So we have to look at how do these gases disperse if we sample them from one point. Is that representative for the whole plume? Are there differences in that? I need to figure out some way of collecting soot because the current gas inlet did not collect any soot whatsoever. My filter that I have installed before these tubes to prevent soot coming onto the sorbent materials was just clean as it gets. So I need some way to collect the soot as well. And that is something that is also challenging for my size of the setup because I do not have this large diameter that creates a very big smoke plume, but I have a still relatively, it's a transition flame more related to or closer to a laminar flame than a fully turbulent flame, so my smoke production is actually not that much. So I might want to look into, if we're looking at in-situ burning, to get some sort of way of producing more smoke than I do right now to make it more aligned with the large-scale experiments. Because now I have some smoke, and if I look at the chemical balance, then I'm basically looking at the chemical balance of my scale. And that is most likely not representative for full scale, but it's a start.
Yeah, I think it's a very interesting setup actually for this application, but it could also be used for other things actually, probably. So I think that's again, you know, it shows that you're not afraid of also trying this, which I mean is the basis. This is a very nice piece of work because I mean you could just leave that out because it wasn't your main field. So I think that's very good. Well, I don't have so much. Yeah. I've had the pleasure of, going to Greenland with you a couple of times. And I know that the firemen in Sisimiut, they were very interested in your herder.
Yeah.
So, when I meet them next time I go there and they say, so what about this Lawrence? How did that go? And what about the herder? Can we have it? What can we use it for? What should I tell them about your work?
Well, I know they were very interested in the herder. It was very interesting to see their response to that thing. I found it, looking back now, I find it quite peculiar, so to say, that they're so interested in it, considering it was so hard for me to get oil up there, because I went there and the idea was that I shipped some of my crude oil samples to Greenland to do experiments with, but there was something going wrong with the labeling or so of the chemicals, so they were held back at customs and were not allowed to be shipped. So I came to Greenland and I had no crude oil to burn. And then I started calling around to get crude oil samples, but the only thing I could find was gasoline and diesel from the local pump station, because that's what they have in Greenland. They don't produce any crude oil or transport it. So I was actually rather surprised that he cared so much about oil spill response when there seems to be so little actual oil activities around Greenland. And when you spill gasoline or diesel on water, I would say that the easiest is just to let it evaporate because it's so relatively volatile compared to crude oils. The herder in itself is not an oil spill response method. You can use it, for example, there has been talking about, and that was their main interest, to spread it between the oil and the surface of the shoreline, and have it as a barrier to prevent oil from hitting shore. But if you don't do anything with the oil, the herder creates a monolayer on the water, so it spreads out and forms a very thin layer of herder. But because of wave activities and over time, the strength of that monolayer starts to break, and the strength of the herder pushing away oil starts to decline. So yes, it will delay oil hitting your shoreline, but it is not a spill response in itself, because the oil will hit the shoreline at some point if you don't do anything about it, if it would not evaporate naturally, that is. Mm-hmm. So what you could tell them is that, yes, it's nice, I think it's commercially available, but it's not a spill response in itself. So if they don't have anything else to combat oil spills, it's rather useless.
Yeah. Thanks. I have one last question. When I sat down, I heard on the row behind me, are you ready to not understand anything for the next hours? So, you know, this is not just a good day for you, also for your family and friends. You know, they are proud of you presenting, answering the questions from the examiners, but they're also a bit anxious, you know, is it doing well? How is it going? And also about the understandability. So I would like you to explain to your family, you know, what do you think is your main result, your main contribution to science in your thesis, so that, you know, they understand, and you can use any language you want.
I'll use English, so the other half of the family can also understand it. The main result is that there were a lot of ideas and so to say hunches, practical knowledge about oil spills. So like if you add more thickness to your oil, you will get a higher burning efficiency. And that was based on practical knowledge, but that is not necessarily true. And what I did in my thesis is show a bit more of the science behind it. Why do things happen the way they happen? And is it indeed what they think happens, the case that it does happen? So does it increase the burning efficiency by just making the slick as thick as you can? No, and I gave a reason why. So going from hunches and ideas and practical knowledge to a scientific foundation that says, this is why it works the way we see it work.
Yeah.
Okay,
yes.
Thank you very much.
Thank you.
Thank you, Gunnar. And we are at a point now that, first of all, we have only about 11 minutes back to fulfill the time schedule into 3 hours of the duration time of the defense. I will ask if some of the supervisors have a question. What about you, Grunde? Do you have any question?
No, I have asked a lot of questions. I think throughout the last 3 years, I'll try to play smart now and ask some things that made me look smarter than I am. I think they exposed me as much as they exposed Lawrence.
So thank you, Grunde, for a clever answer. And Janne Frit, do you have any?
No, I can just...
You agree with Grunde?
I've been very exposed by my co-supervisors also.
Okay, thank you. Because we also have now room for the audience. There's one question left from you, I guess. Huh? And your name is?
My name?
Yeah, your name.
Oh, my name, Tosca.
Okay, please.
I have a question about the chemical herders. You use them to capture the oil in order to burn it. But my question is, what is the chemical herders, are they bad for the environment? And is there any way to remove them from the surface if necessary?
You should actually ask. No. The idea behind the chemical herder is that you need so little of it. You use 150 microliters per square meter of oil, that relative to the damage the oil spill does, it's negligible. that is what the producers of the herder say, and that might not be the case. So there are toxicity studies, and how toxic is it? I have not conducted those studies myself. I think they're still ongoing. Yes, there's definitely some lobbying involved. With respect to removing it from the water surface, I would say, apart from it naturally happening, no, you cannot. What I see from burning oil is that if you apply a herder compared to a normally thickened oil, is that the herder adds a bit of a dull gaze over the oil that when you ignite it gets removed. So it seems like the herder also burns, but because the layer is so thin, that does not spread over the rest of the water surface. So the only thing you can do is wait until the monolayer of the herder starts to break up and dissolve in the water column, where it may or may not be biodegraded.
Are you satisfied?
Very satisfied.
Thank you, Lars. And I have some final conclusions here. The subsequent procedure of the recommendation is now that the assessment committee prepares a recommendation as quickly as possible. It's you three guys. And after that, subsequently the PhD committee will process the recommendation, and finally the degree will be awarded by the dean on behalf of ETU's academic council. So, for now, I will declare this defense proceedings to be concluded. Thank you very much.
Thank you.